Hello, welcome back to our CSCI for 30 operating system, and we'll continue the next part. The chapter is about memory, but before that, I would like to recap what we talked about before. First one, you need to remember is the fetch cycle. So if you remember, we talked about the PCIR. Okay, which is most important. You need to know the sequence. And um, you ask some questions, and then when you work on the assignments also related to this like fetch stage and execute stage. Okay, so um, once we fetch instruction. Okay, so inside the CPU, which is what's the program counter is stored. So remember, so the program counter is the memory address location, and every time when we go to move on the execution stage, then we'll plus one. Okay, automatically plus one. And also we have the AC, okay, accumulate counter. So that when we adding the value, okay, so no matter you are adding minus, okay, so all this will be stored into AC. And also the IR is the instruction for this one is storing the memory address. So we'll go to which memory location, okay, to fetch. And also we have the operand, okay, that means like are we going to add minus, okay, or store or low. So all this will be stored under the IR. Okay, so this one is important. And then next we talk about like different type of interrupt. Okay, so we do have like program interrupt, timer interrupt, IO, and then also the hardware failure interrupt. And just telling you, maybe if you look at nowadays, using the current computer idea, you're thinking, yeah, it is pretty common. But for the really outdated design, really long time ago, so they don't, if they didn't design like without interrupt, we have to wait for the IO input, wait for compute. Okay, so it's then no interrupt, but when we have like short interrupt and then just have a shorter IO wait, okay, so we go back, okay, waiting for next interrupt. Okay, here's the idea for interrupt. Okay, after we finish this part, we will move on to memory. So basically, when we talk about memory, okay, so we will try to list and describe the type of levels of characteristics of computer memory. And also we're going to talk about some like concept related to like locality and also analyze the performance of multi-level memory hierarchy. Okay. And next, we try to understand the operation of the stack and use a support the procedure, call and return. So that's where we're going to discuss about. Okay, so when we talk about the memory hierarchy, okay, right here, the major constants in memory, we will talk about like the amount, okay, what size, and then the speed, also the expense. Okay, so here's the three constraints that we're going to discuss related to memory, and also memory must be able to keep up with the processor. Okay, it's important. And also the cost of memory must be reasonable in relationship to other components. When we talk about the main memory, okay, maybe the some like cache, also those memory or secondary memory. So like this. So we need to know the terms. When we talk about memory, because they are like faster access time, greater cost like per bit. Okay, and also if you look at the price, like about the memory. Okay, sometimes they do have a frustration like going up and down. Okay, depends on market, and also you need to know like greater capacity, smaller cost per bit. They like they try to produce. Of course, nowadays the tennis, okay, we can produce like we're putting higher, just like even a smaller size, okay, same size, but we can provide more memory. Okay, so also we given a greater capacity, slow access speed. So it should be make sense, right? So if we have a higher capacity, that means we need to like go through all the memory. So maybe the access speed will be lower. Okay, so here's the relationship between all this memory. Okay, and when we going down from the hierarchy, so we need to know like when we from here, like decreasing the cost per bit. Okay, just remember, and then we will increasing the capacity. Okay, and also increasing the like access time. So all this, but here the last one here we try to address is that we try decreasing the frequency of the access to the memory by processor. So here this part is pretty important when we talk about memory and then the CPU like access. So here's like the frequency, just they focus on frequency of access. Okay, so remember we can decrease it once it goes down. Okay, so just remember this part and just giving you I have a graph right here. So it kind of like showing the performance of the simple if we have two level memory. Okay, so just like here's the fraction of like access involving only if there's one level, okay, compared to the average access time. So right here you see from 0 to 1, okay, within the hit ratio 0 point something, okay, the time, and then we will see like I think T1 to T2 here we're adding together, dropping. Okay, so you will see the performance like going like this, okay, and then we in the introduction we talk about one is the locality. Okay, so where's the principle of it? So the memory refers by the processor. So is they tend to like cluster, right? So the data is they organized. So that the like percentage of access to each successive lower level is like substantially like less than the level above. So it's that like the purpose we try to do like when we try to organize it, and also can be like applied across more than like two level of memory. Right now, maybe you are thinking like what's the two level memory? Okay, so what we are talking about, like what's the two levels? Okay, later we will show you what's the two levels of memory. Just like right now, you just need to know what okay about this like principle. Okay, of the locality, this one. And then another one right here, we move on, is called the cache memory. So it's invisible to the OS. You need to know one feature is that is in cache is invisible to OS, and then it interact well with other memory management hardware. Okay, so processor must access memory at least like once per instruction cycle. So that's what you need to know because we need to load the instruction from memory to CPU, right? CPU, then we can process it and return the result and somehow back to put it back to memory. Okay, and processor also the execution is limited by the memory cycle time. So this one is like kind of just need to know. Okay, it's limited to the cycle time, and also it's expose the principle of locality with like a small and fast memory. So just like remember about this one. So this one is like the about the data. If we like so the percentage of access, like the successively like lower level will substantially less than the level above. Just remember this part. Like what's the linkage with this? And just like main focus small and fast memory. So that's why when we design the cache, if you know have some idea, so that's why the cache memory sometimes like attached to the CPU. Okay, directly attached the CPU or the coder, and it always come with the a smaller size, but it's like faster access. So it can contain a copy or portion of the main memory. Okay, when we talk about main memory, that's the RAM. Okay, so sometimes when we say that main memory, second storage, that means like main memory is the RAM. Okay, and the second storage, that means the hard drive. Okay, and because the cache memory is way faster, like processing faster than main memory. So when we have a copy of portion, then processor can like first check the cache. So if we find it, we can just like grab it from the cache. So it's like way faster. And also one of the feature of cache is that it's smaller size than main memory. So we cannot like put the whole copy. So it's only portion of it. If not found, then we try to like getting a block of memory. So it's read into cache. So if we need that block, okay, so if we couldn't find it, then we try to load that block and then read it into the cache. Okay, then we can prepare for it. And also because the locality of a reference, so it's likely that, okay, in many of the future memory reference will be to other bytes in the block 2. Okay, let's remember this part of the about cache. So then right here I'm giving a graph to showing you we have the main memory, so it's the RAM. Okay, so if we have a single cache, so when we load it, it's pretty slow, and then we transfer it in a block. Okay, so we save it in cache. If the CPU need to load the instruction first, we go to like find search it in cache. If we do have it, just like okay, so we can send it to the CPU. Okay, it's saying by the word. And if no, not found, then we will try to like transfer a block of it into cache and load to the CPU, and then we can save it into the cache. Okay, so in case later you will learn we do have some mechanism. Okay, so I want to talk about like how can we swap the block, right? Because like, okay, we have frequently access those. If something like how can we replace it? Okay, and then which part of the memory should be like being replaced like to the cache. This later we'll learn about. In this moment, you just need to know. Okay, we're doing in this way. Okay, but what's the mechanism? Like how can we choose? Then we can hold this part for later. And then we have like we talk about 2 level, and right here 3 level. So if you see like L1, L2, L3 cache, so actually it will be look like this main memory, and then we have the level 3 cache, okay, and then level 2 cache. And when you see the number level 1, which like the closest to CPU, actually some like we say L1 or L2, sometimes they will be like exactly attached to the CPU. Okay, and sometimes like level 3 will be like come between the motherboard. Okay, so we have the cache memory. So here's the design, like physically on the hardware motherboard. That's how we decide about the cache. But of course, those cache really have a small size. Okay, and when we look at the cache and main memory structure, so we have the line number, we have the tag, and comes the block, because we're loading those block to the cache, right? So we have a K-works. So when we're loading the word right here, so we load the word to the CPU, like just like the instruction. So here's the cache. And main memory, we have the kind of like we have a certain a block right here contains a K-works. So we'll load this block to the CPU, the cache. When the CPU need like certain instruction and then execution, okay, and when they try to fetch it from the cache but couldn't find it, then we try to load it from a main memory, and then we will keep it in the cache. Okay, this is the idea. So we like moving it and then swap out, and then move a new block and then save it into the cache. So here's like how it works. And here so far is like the cache I read operation. So when you look at this part, so we try to see, okay, when we try to start, sometimes when we doing the operation, so we have a start point, okay, and then, or sometimes we put the end. RA we're showing the read address, just like, okay, so we try to receive the address, RA, the read address from the CPU. And we should first we search, okay, is the block like containing RA in cache? So check. Okay, if yes, of course, we just like fetch the RA word and then deliver to the CPU, then done. Okay, pretty fast, right? If no, then we have to access to the main memory, okay, for that block containing the RA, and then we need to allocate the cache slot for the main memory block, okay. And here you see like simultaneously, like actually there are 2 things, like they will be going to execute one, deliver RA word to CPU, and also load main memory block into cache slot. So they are not like waiting for it, but we try to like doing the same time, just like copy and load, okay, in the same time. Okay, so will be like this. If you are interested and we have any question, then you can look at it and answer the question, and you will see. And the next, after we finish the memory, have some like quick idea, just like if you remember. All this we talk about, one is cache and then the one is the memory, and then we talk about like 2 levels, and then there's like 2 level with a single cache, or 3 level cache organization right here. So L1, L2, L3. So That's the idea we using the cache and then the main memory. And the next one we will talk about is the multi-core computer. Of course, within like really long time ago, we do like talk about like single core, but nowadays multi-core is a must, right? Okay, so we need to know what's the basic characteristic of multiprocessor. Okay, and then what are the like multi-core like organizations? So that's what we need to know. And if you're ready, then let's go on. So multi-core computer, so we'll know just like it's the chips like multiprocessor. Okay, so that means like inside there's a processor, so many. Okay, so sometimes we combine two or more processor. Okay, that's we talk about the core. Okay, on a single piece of silicon. Okay, okay, right here. So each core consists like all of the components of independent processor. So we put them together, and also in addition, so multi-core chips also include the L2 cache, and also in some cases like L3 cache, right? Um, when we talk about it, we have the L1, L2, L3. Okay, so it's possible, but depends on how we design. So we're going to put all the cache in that CPU. So if you know the size of the CPU, then of course we cannot put the cache large amount. Also, when we learning like computer, actually one thing is about trade-off. You say, how about just like put the cache, okay, like exactly same size of cache as a main memory into a CPU? Yes, it's possible, but the cost, okay, the size of CPU, okay, it will be like maybe rapidly goes up. So we need to have a trade-off. Like we need to decide what's the best size, provide helping the processing efficiency, but with the lower cost. So that's what we need to think about it. If you know, we have like i7 core, of course, like right now we have like i9, and then maybe AMD, they have their own design, or like Apple, like their um M1, M2, M3, so they are different type, and then including the GPU. But we don't have to like make it kind of like off topic, but we only talk about the CPU like multi-core, and sometimes we talk about like Intel core or Windows system. That's what we learning operating system. So for all these like cache, including the core, they come with the L1 cache, L2. Okay, you see the right here I want like 32 kilobytes. Okay, so or the 256. Okay, and then they will share a slightly larger like L3 cache, and then they will have a DDR3. Oh, right here you see it's like DDR3 memory controller, but now they support like DDR5. Okay, so pretty common. Or later, like we have the DDR6. So, but here's the design. You see right now core attached with the cache, so they will have their own cache for each of them, and then they have the level 2 cache separately, and then they will share their or like L3 cache with a larger size because we have to share them together. Okay. And we talk about the multi-processor, okay, multi-core. So one is called a symmetric. So it will be the standalone computer system with following characteristics. So we have like two or more similar processor. They're like comparable, like capacity, okay, capabilities, okay. And then those like processor share the same main memory, and they are interconnected by a bus. So when we talk bus, actually is it's a channel like connecting different hardware, okay, some other internal connection schema, okay, so it's called bus, okay. Those like processors share access to the IO devices, and all these processors can perform the same function, so it's called symmetric, okay. And the system is controlled by an integrated OS, so this one is a multiple, okay, multiple processor and networking together is called symmetric SMP. So you see, we have the processor 1, 2, 3, and then of them they have the L1 cache attached to them, and then we have their own L2 cache. Okay, it's like out of the CPU. Okay, so they all connect by the system bus. Okay, channel, and then connect main memory, and then the I/O. Or this, then they can share their functions and work together. That's how it looks like. It's like called SMP. You're thinking it's kind of like stupid, okay? What you putting? But in the old school, if you see some pictures, we do like on the big motherboard. So you have like 2 slot or 3 slot to put in the CPU. So also it performs multi-core or multi-processor, right? So we start from this, and we talk about multi-core, and then the next one is about the direct memory access. So we try to introduce the concept like what's the direct memory access and how can we use in computing like system. And when it's like called the I/O access. Okay, so there's 3 techniques that are possible like for I/O. One is the program I/O, interrupt driven, and then also the direct memory access. Okay, so that's what we're going to talk. For the program I/O, so when a process encounters like I/O, okay, so I/O means the input output. So no matter a keyboard, a printer, okay, a monitor screen or any like it's an I/O. So it executes and the instruction by issuing a command to I/O module. Okay, so those module, okay, so will perform okay the request action and says like the result bit. So it doesn't really interrupt the processor. It's just waiting for the result bit. And then processor may take some of the active role in determine when the I/O is complete. Okay. So the processor will like periodically like checking the status of the I/O module. If you remember the interrupt, okay, so if you remember the interrupt, then we try to like wait for the I/O input, process done, we go back. So, but this one is called the program I/O. But how about the interrupt-driven I/O? Processor issue the I/O command to modules and then continues doing other work. Okay, because like for I/O, or they have a module or we have their code driver, okay, to complete its job. Okay, then we kind of example is like, okay, it's like doing asynchronous, we don't have to wait on result. What's example? Let's say printer. If we have to do it like program I/O, that means like processor need to send a like printing job to the printer. We have to waiting for the result bit. Okay, once we complete the printing, if we turn it, then the CPU have to like go back and check. Okay, it's ready. So periodically, okay, periodically like I'm checking the status, right? Okay, if we say, okay, it's done printing, then I can go back to the normal job. But for interrupt, no, I don't have to. After I send the printing job, I can go back to my original like task. And once I reset the interrupt from the module, I say, okay, it's done not printing, then maybe, okay, I will go back and check like this. Okay, so when finished, the I/O module will say interrupt to the processor. So request service when it's done or ready to exchange data, something like this. Or like the scanner, okay, if we the CPU like try to issue the command, like say please scan, okay, then you don't have to wait for the scanning complete. Okay, so you can like go back to process other instruction. And once we receive the scanner interrupt I/O, say okay it's complete, then we maybe have an exchange like we can retain the buffer from the scan the data from the scanner. So it's called the interrupt-driven I/O. And the one we talk about was direct memory access. So when we have a large volume of data able to be moved, so we try to use the DMA is a direct memory access. So it's more like efficient. So what's the more efficient in it? Because like both the I/O setup, okay, and then transfer data controlled by the DMA I/O modules. So you just thinking we talk about module or we talk about like driver, so it's same. So it's like overnight the DMA use or need some special processor to control the transfer and negotiate usage of the system bus. If you know the system bus, it will if you took most of the bandwidth, okay, it may slow down. So we need to talk about that. The advantage of it is when you try to copy the file, let's say from your storage SSD to USB to maybe your hard drive. Okay, so if we have the DMA, direct memory access, so using the driver or sometimes we have other special processors to handle it, then we don't have to wait. If you had to wait for the file transfer complete, and then you need to and then your CPU to take another instruction. So it's kind of like wasting, right? You're just like waiting for it for complete the file transfer. So it's better than just like let the modules to handle it or something. Of course, maybe we need may use a special processor to control the transfer or negotiate the usage of the bus. For other than just like regular our CPU multi-core, we don't have to wait for that. Just keep on processing other instruction is good. So it's called a DMA direct memory access. So far, we go through all these like conceptual idea, okay, of this. In the beginning was the elements included processor, main memory, I/O modules, system bus. We'll talk about that. And it's important learning like OS is the instruction execution is the fetch execute cycle. Okay, we have a basic one. Okay, and also later we will learn about what's the interrupt. Okay, how the interrupt like processing and memory hierarchy. Okay, so remember what's the decreasing speed and the course like goes up the hierarchy like that. And also we have the cache. Okay, but those cache beside L1, L2, even L3. Okay, and also we talk about like multi-processor. Okay, multi-core. We talk about like the symmetric one. We really have identical like processor put them together. But nowadays we say multi-core is like one CPU. Okay, or they contain like multi-core inside. Okay, and also it comes with the like L1 cache. Maybe like on the motherboard we're attaching like with L2 and the L3 cache. Okay, so here so far that's it for our first part of our lecture. Okay, so later I will have another new chapter. Okay, thank you.